So thank you. You will see the outline here, and I thought I will start to just give a quick background about me, some quick numbers about Spotify. I hope most of you know what Spotify does. How many is using Spotify right now? Oh, okay. That's a lot of people. But we are a very tech-driven company, and we are very proud of that. Some quote, I think, by Daniel, the founder, was that we are a tech company in mind, but with music in our heart. And that's certainly true for us. But I'll try to speak a bit more, what we use all our data for, and especially a bit more about the architecture and the backend systems we have to be able to do that. I thought I will focus partly on some batch processing and how we can do that, and also some more streaming, real-time processing techniques that we are making use of. In the end, I'll just go through a couple more advanced analytics use cases. But just to see how many of you have ever used, for example, scikit-learn? How many of you know what collaborative filtering is? Okay, so I won't go in too much into the machine learning stuff. But feel free, by the way, to ask any question. I think it's so much fun, for presentations to be interactive. Just as data visualization should be interactive nowadays with Tableau, etc. I think a presentation should be interactive as well. So if you have a question, just raise your hand, and we'll try to manage that. I have a background from academia, started there, continued for a while doing research in Swedish universities, but kind of quickly went into more startup businesses, but been working basically with machine learning for 10, 15 years in different areas. But in the last 3 years, I've been working at Spotify. And we have recently made some changes in the way we organize analytics specifically. Previously, we were a larger centralized analytics department that tried to help the different parts of Spotify in their more analytical needs. Recently, since last year, we've decentralized a bit of the analytics work, so people are more embedded into the different functions that we have in Spotify. And functions can be something like marketing or recruitment or the legal department. And of course, all the different products and product squads that we have. We have a huge number of about 100 different small teams working with different function or cross-functional tasks within Spotify. But recently we have this decentralization, and we also have a couple of core analytics groups around. And one of them is more for engineering, more data engineering work. Another one is for more data scientific or research work, and that's the group that I manage here in Stockholm. And in this research group, we're trying to tackle problems that are foundational and common for a lot of different parts of Spotify. But also are perhaps in need of a more in-depth analysis that requires some long-term projects to be handled in hopefully a bit more scientific and academic way. And to give you some feeling for the size of Spotify, these are a bit old numbers. We have about 75 million plus active users. If you saw yesterday, we actually announced that we passed the 30 million mark for number of subscribers, so that's a very recent number. And we are in about 58 different countries right now. And for the actual catalog, we have about 30 million licensed songs that we can play on demand. And this number may be a bit hard to really interpret, because you may have heard some other companies saying they have 100 million songs in their catalog and are bragging about having this huge catalog of different songs. But when you look in reality to the songs you have, we actually receive a lot of songs from the labels and from other artists and companies, and they actually deliver really noisy and low quality data for the metadata of the songs. So we have to do a lot of cleaning. We have to deduplicate the songs and disambiguate artists. And we're really proud in doing that. And that's one of the areas where we require quite a lot of more advanced machine learning tasks to be able to do this in an automatic way. So these 30 million songs is really the properly deduplicated number of songs that we can play on Spotify. In reality, just taking like one song like Get Lucky or something with Daft Punk, we can I think we have like 300 copies of that song in our catalog. Imagine if we didn't do any duplication for all these songs, we could say we had, 1 billion songs if we wanted, if we didn't count this properly. But we don't. We do receive a lot of data, for one from the different clients that we have, and also from all the different backend services that we collect and store in a large Hadoop cluster. That is about 2,000 machine node cluster with about 100 petabytes of data and 100 terabytes of RAM capacity that we can use to run all our jobs. And I think we run about 10,000 jobs per day in this Hadoop cluster. Besides the Hadoop cluster, we have a lot of other clusters. We use a lot of Cassandra, for example, so I think we have like 1,400 nodes just for different Cassandra clusters. And a lot of other backend services as well. I have some exciting news that I'd like to share as well with you shortly, but I'll keep that for now. So what do we actually use all the data for? A lot of people think the only thing we do data analysis or machine learning for is making recommendations, and that's really not true. So we need to, for one of the more critical stuff we need to do is report the usage and the streams that we have for all the artists and the songs to the rights holders, the labels. And that requires quite a lot of data crunching in our Hadoop cluster to perform with stability and quality. We, of course, have all the different features like the browse feature, the search, radio, etc., that all have the separate needs to be able to function. For one, to clean up the catalog, and for radio, for example, we need to do the collaborative filtering and machine learning necessary to be able to recommend the proper music. I spoke briefly about the catalog. One thing I should mention, we're trying to be really data-driven in that any change that we make, especially in a client, we want to A/B test that. So we take perhaps 1% of the users in a small test group and another % of users that could be in a control group that we guarantee are having the old experience. And we try to measure and perform some data processing and being able to, with significance, understand and be assured that this was really an improvement in the user experience for a certain change that we made, for example, in an iOS client. We also have, of course, a lot of more business analytics going on, a lot of KPIs that we track and measure and try to understand and break down in different ways and through different dimensions. In reality, I would say what we are trying to do is not just make recommendations, it's really about trying to understand our users in a more holistic way. By having this more deeper understanding of the user behavior, we can, for one, improve the different products we have. We can also, of course, make better recommendations. But having the holistic understanding of the user is what really is key to be able to deliver in high-quality services. I just recently added this slide. We actually had a data art computation. Sometimes data science can be really fun. I guess most of you can't really see in the back what this really means, but let me quickly describe it to you. This is a set of employees actually at Spotify and their listening behavior. So each line is a session, a set of tracks that the user played at a certain point in time. And then they are trying to measure, this is basically the beginning of the session, and as you continue, you either go more for familiarity, that is more popular songs, or you go more for a discovery mode, playing songs that you are not familiar with and are potentially less popular. So then you can see and visualize how some users behave. You can see that this have kind of an average behavior. Will, for example, in this case, is very into listening to familiar songs. And Rochelle, for example, is very much into discovering new music all the time. So, visualizations is really cool, and we can do a lot with it, and it can even be art in this case. This is another example of one of the submissions in this data art competition we had recently. It's a bit more difficult to understand, explain what this is, but in reality it's about 100,000 users in a user cohort where their behavior is being averaged, and then we're taking 2 or potentially 3 fields and visualize them in these different 2D shapes. So this is basically a particle trail that you can follow throughout 1 week of these users listening to different songs. So in this, I think the first one was basically looking at the number of skips versus full plays and half plays or partial plays. And with these potentially simple data fields that you are looking at and trying to understand and explore, we can actually find really beautiful visualizations for them, even though this one may not be the most useful one. But it's cool, right? Right, thank you. This is a traditional graph, but I'd just like to quickly explain, when we do an A/B test, this was a test where the purple or orange one is the control group and the blue one is the test group, and we are measuring one of our KPIs, which is the second week conversion KPI, basically how many people that convert to premium after a certain period of time. And in this case it's with clear statistical significance that you can see the control group outperform the test group. We would never launch this feature with this clear data. So seeing this data after having developed a new feature for a couple of months is not a fun thing. But this is very common, and this is the reason we're doing A/B tests. We want to be sure that a new version, a new way to visualize perhaps the client in a certain, in the web client, in the desktop, in one of the mobile clients, or even some other embedded client, we must make sure that people actually do appreciate and think the experience is improved. I think I'd quickly go through this. The point of this is really to confuse you all and make you less understand this presentation less. But what a lot of people think when we hear Spotify is basically just the different, mobile apps and clients that we have that we used to play on Spotify, but in reality we have so much more. This is just the tip of the iceberg. So, for example, this purple circle could be the Android mobile app that we have. And then we have a set of different other apps, but they all access data, and they want to be able to find the music to play. And they want to send requests to some backend service, for example, a search service saying, find me all the artists with Rihanna in the name. So all of them send some kind of request, and we have what we call an access point that redirects that request to one of all of the different backend services that we do have. This is a gross oversimplification of it. We in reality have like hundreds of these backend services. But one backend service could be, for example, the search service. Another one could be the browse. We have the playlist service, etc., that we can access. And all of the data that we do, try to store, we get it for one from all the client, but all the services send data to our big Hadoop cluster that we're having, and then we can do more analysis on that. And then we have, the music is stored in different areas in different ways. But we try to store a lot of log data for different client behavior and also service behavior that we see. No questions so far. No, that's boring. I think I'd do this rather quickly as well. This is just taking one of all the backend services and focusing on that. So if you zoom in on one of the pipelines, this is the discovery pipeline, not the discovery weekly that all people think of. This is the other one with the discover page that can show you that you perhaps would like to listen to this artist because you listened to that and that type of artist before. So they're trying to find recommendations because of previous listening behavior. So we have something called Luigi that we developed in open source at Spotify that is helping out with scheduling a lot of jobs running on Hadoop or on other services. And that Luigi can also not only do scheduling, it can also actually run, and you can write the MapReduce jobs in Python code if you want. But you can also run other like Spark jobs, or we use a lot of Scalding and Crunch especially at Spotify as well. And they can all be scheduled with dependencies, making sure that if you run a certain job that are dependent on 3 other data sets, make sure that they are finished before running this specific other job. So a very crucial and important part. running a lot of different jobs through our cluster. We put a lot of data out of this processing into some kind of online distributed database, and we use Cassandra a lot for that. And from that database, we can have some kind of backend service. In this case, it's called Bartender. So that's the discovery backend service, which can produce recommendations. So this client more or less directly speaks to the different clients that we have, some mobile app or web app or something. And that in its turn send more data into the Hadoop cluster. And we basically have a feedback loop where we can continuously improve the recommendations and the performance of this pipeline. Everyone is still with me, I think. But we are facing some problems, and we have some news. This was actually announced like 2 or 3 weeks ago, but we are having a lot of problem with our on-premise cluster, so we are having a big collaboration with Google Cloud. So we will move more and more of our job and processing from our on-premise 2000 machine cluster into Google Cloud environment. The reason for this are multiple, but one essential problem is that we can't really store the data that we are taking in, and we can't delete the data fast enough for us either. So we basically we can calculate a date where we will run out of space in our on-premise cluster, and that will basically shut down our service unless we do something about it. That's why, if we instead do a lot of processing in Google Cloud, we more or less have infinite storage capacity in their environment. And some people may ask, why don't you simply add more machines to the cluster? And we can, and we have done so in the past, but at some point in time, you can't add more physical machines to the same cluster. You need to either split the cluster or move the whole cluster or do some more drastic change. And that is a really difficult change to make. So we are betting in that we don't have to do that by moving into a cloud environment instead. And Google also have some other interesting concepts, like they are trying to decouple compute from storage. What that means is we can basically forget some of the slogans that a lot of Hadoop users have tried to put into you before, that is data locality. Basically saying that the data should be very close to the algorithms. You shouldn't have to send the data over the network to be able to process it. But in Google land nowadays, that's not the case. So they have their own networking equipment and can apparently send the data fast enough, so the network bandwidth is not in reality a bottleneck anymore. So the need for data locality is removed. That makes it possible to separate the storage services from the compute services, and also scale this in a more efficient way. I guess this is another of the confusing architectural pictures, but we're kind of proud of this, and this is a work in progress still at Spotify, but we want to have a common environment where we can run jobs both in our Hadoop cluster, the on-premise cluster, and in the Google Hadoop cluster as well. So we have something called Hydra that we're working on that allows you to write the job once, and then either run it on our on-premise cluster that we have, or in the Google Cloud Hadoop cluster. So Google Cloud has something called Dataproc that allows you to easily fire up a new cluster and then run the job there and shut it down when done. So that is what we can do, and we can basically fire up and shut down clusters on demand instead. So we don't have to have a permanent cluster running that everyone is sharing. Then we have some cool support. I have to add this. We have a Slatinator as well in our. Yeah, it's wrongly spelled, but it's still it's still supposed to be Zlatan. Yeah, it's nice that you noticed the misspelling. That's something everyone is complaining about at Spotify as well. Can't you even spell Zlatan? That's bad. So that system was more for batch processing, and we also have a new system for doing more real-time streaming processing. We have heard today a lot of talks speaking about Kafka and systems for managing log data in real-time fashion. In Google Land, they have something called PubSub, which is similar to Kafka. And we have some systems that take the data that we get from the clients, could be a mobile app or something else, or it could be from some backend service. We send that through our own system called Pulsar that will aggregate and split and process the data, transform the data a bit, and then put it into our PubSub or Kafka similar cluster. Once we have it in PubSub, we have a lot of different other services that can, on demand, choose to subscribe to, for example, all the data for, we have something called end song. That's basically every time the user finish playing a song, an event is sent saying, okay, now that user at that point in time streamed that particular song. So that is causing one event, which is one of the more common and most used data sets at Spotify. And this is about, we have, how many is per day? I think it's about 1 billion per day of events coming in this data set. So that, I think, is about 10 to 20,000 per second of streams being processed. And then we have a lot of other topics as well being streamed through PubSub. So hopefully this will make it easy for us to develop and add even more real-time systems in the future. No question for that either. Okay. So what do we need real-time systems for? I'll try to be a bit more concrete and show some examples of how Spotify could use some real-time processing. For one, of course, we have real-time dashboards, and just to give one example of why it's necessary to have, or useful to have, real-time dashboards, we of course had thousands of dashboards before as well, but having them real-time can be a big benefit. Imagine us releasing a new version of iOS, an iOS client. One thing that we would like to see as soon as we release it is the number of crashes that occur. We always have a number of crashes, but if we have an unexpected bug going through all the testing and every other type of preventive action that we take, we want to be able to quickly see that this new version is severely causing a lot of crashes in the clients. We don't want to wait one day for that to happen through some batch processing system. We want to be able to see that live. So that can be one big benefit of having more real-time dashboards. Recommendations is also something that we want to have in, if you imagine a new user coming into the service, perhaps a user have just registered for Spotify, never played anything on the service before, then we don't have we have no information about that user. We don't know what the user would like. Okay, I spoke too much, I guess. Anyway, having more real-time recommendations to onboard users is also very important. Just quickly about one thing that I'm also involved with a bit. This is the number of streams for a specific artist, specifically David Bowie. Can anyone guess what happened on January 11th? He had very few streams here, and then something happened that caused a huge spike in the number of streams from Bowie. He died, yes. So this is that. If we could find these kind of trends and patterns, that would be an interesting thing for us. Okay, I think you heard all about this new type of analytics before today, so I think I skipped most of it. And talk a bit more about fun stuff. How many minutes do I have left? Okay. 7 minutes, okay. So let me ask you a question, try to make you interactive by forcing you to answer some questions. I could either go for how we produce recommendations, this is actually not as complicated as you think. I think I can explain in 2 minutes how we are producing recommendations. Could also go a bit for if you want some more deep learning context, and one use case that we use deep learning for. Or another one, this is a more end-to-end Spark pipeline trying to predict a certain behavior on the users and using a set of interesting tools. So if you were to choose one of these, which one, if you ran, just raise your hand for the one that you're most interested in. How many is interested in the collaborative filtering and recommendations part? Okay. And deep learning. Oh, it's about the same. Shit. No, and the Spark end-to-end. Okay. Okay. I think I choose simply what I think is most interesting then. Okay, I'll skip this one. I very quickly go through the deep learning thing, and then I take a couple of more minutes on the Spark end-to-end pipeline. So the use case for this one is, when we want to make a recommendation, we basically collect information about all the tracks that has been played at least 500 times. So some number of users has to have streamed each song in a catalog at least 500 times to be able to be recommended through the normal recommendation systems. If only one user has ever streamed it, we don't have sufficient amount of data to properly produce a recommendation. So that's a problem. I mean, how do you recommend new music coming in? We get 20,000 new songs every day. We want to be able to quickly recommend it, otherwise it will be hard for them to actually get any traction. So one approach for that could be to just look at the raw audio data of the track. Instead of looking at all the usage patterns that the normal recommendation engine do, we can just look at how the actual raw audio data looks like. And with that, we can try to predict. In the end, we have this 40-dimensional vector, which is basically what we want to get out from the normal recommendation engine. But instead of looking at all these usage patterns that the normal recommendation engines do, we just look at the audio data. And we have a lot of training data to train this deep learning network on. So just looking at the raw audio data, we can try to predict what type of music this is. And then once we have this data, we can still recommend that music just because of the way it sounds, not because of who has listened to it. Well, I can't go into detail about any specific function, but no. But if you would have continued the questions there a bit, I would have simply said, I can't talk too much about the specific details. Cool. So let me spend a number of minutes on this one as well. So let me first try to describe the business problem that we're trying to solve with this pipeline. And in this case, we want people to convert to premium, because that's really where you have the best user experience as a user, and we also make more money as a service from Spotify. So today I think we have about 20% of the active users that do convert to premium. And a lot of users do convert to premium of their own free will. They are tired of seeing ads, or they want to have the download experience or something else that you only have in premium. So they convert without us taking any kind of action. But some users don't. Some users don't convert of free will. And then we can target them with some either ads specifically for that. So they hear some ad saying, aren't you tired of these ads? Having an ad to say that you're tired of ads. That's kind of good. Or we have some other notification system we can make use of. But then we want to minimize the number of these ads that we show. So we want to have as few number of ads that we have to show, while still retaining as many conversions of users into premium as possible. So this is a difficult problem to model. It's kind of easy to just try to, if you think of this blue circle as all the users that we do have, it's rather easy to build a machine learning model that tries to predict if the user will convert or not. So it's a simplistic classification, like logistic regression model that we can build from this. using a number of different features, describing the user demographics, behavior, and other type of data. But that's not really what we want to predict. We want to predict that a user will convert to premium because they actually were exposed to this ad. That's a much more difficult problem. And this is something called uplifting, if you heard about this. But you can think of it like if you had two test groups, one test group with random users, another test group with the best users that are eligible for this type of action, and then try to find what user should you put in this high targeted user group to make as many of them convert as possible because they were exposed to this ad. So that makes it a whole lot more difficult and interesting, at least from a data science point of view. And using this, we have a number of steps that we need to do to be able to build this machine learning model. Just extracting the data is, one of the most difficult things to do, and certainly the most time-consuming when you run the pipeline. And it's certainly something that we need some serious computational power for. But once you have that, you can often just sample down the dataset. If the goal is first to just train the model, you rarely need the full data set, all the users to do this. We don't need, hundreds of millions of users to be able to do this. We could just take a small sample of perhaps 10,000 or 100,000 users, which you can actually train in scikit-learn or in some non-distributed tool, potentially. The question is what quality that would lead to, but often you can at least sample down and reduce the computational needs for that. But you still need to do the data extraction first. Then you can do sampling. Then you need to build all these features in a nice, normalized way. And then you need to do the actual training and some evaluation of the model. So that's nice. Then we have a model that is trained, and you can start making predictions with this model. So in this step, we need, in this case, to go through basically all the users. In comparison to the training phase where you can sample down, we can't really sample down in the prediction use case. Now we need to go through all the users, apply the previously trained model, and estimate this probability of a user converting because they will be exposed to some ad. So basically the same set of steps needs to be done for all the users in this case. So data extraction, feature building for all the users, that's super expensive. Doing predictions for all the users, yeah, that's also rather expensive. And then we need to do some kind of sorting or selection of the users that have the highest probability. Yes. So we rank the users, and we can basically take the top X thousand users and expose them to this kind of ad, upsell ad. Awesome. I think that was it. So thank you very much for your attention.